This is the integrated 2 polygons review before our last essential skill. Need to know. There's a whole bunch of stuff you need to know for this one. You got to make sure that you know the vocabulary words for the different polygons. Additionally, you need to know the vocabulary for the polygons inside them as well, so the apothem and the radius. You need to know what a regular polygon is as opposed to just a polygon. How to find the sum of the interior angles, the measure of each interior angle in a regular polygon. We can't do it if it's not regular unless there's a picture that's given to us. The sum of the exterior angles, each exterior angle of a regular polygon. Again, unless of course the picture is given to us, then we can calculate that. If it is not regular. The area of a triangle, which we know is base times height divided by 2 or half base times height. Area of a regular polygon, and then the vocab, and then the ratios also. So it's kind of a lot that we need to be able to do here. So if we take a look at question number 1, got some examples, tried to organize this as best I could based off of the concepts that were just listed on the first page. So I'm going to calculate the sum of the interior angles. All right, so I wanted to do one with a picture here just so you can see kind of the process that I go through. So pick a corner. It doesn't matter which corner you start from. So if I start from that corner, and we want to dissect this into triangles. We're going to connect to all of the other corners that actually create triangles. This is where this comes from. Now, if you understand where this comes from, then it's not really necessary for you to go through and draw the different triangles. However, hopefully this will clear up for you why we might have some confusions. All right, now we want to go ahead and count the triangles themselves. So we've got 1, 2, 3, 4, 5, 6, 7 triangles. Now, if we know that each triangle is going to give us 180 degrees total, and we have 7 triangles, then we're going to do 7 times 180 to get the sum of them. Now, there's another way to actually come up with well, how many triangles are we going to have? It's based off of the number of sides that your polygon has. So if we go back to your polygon and we actually count the number of sides, so we know there's 1, 2, 3, just kind of working my way around, 4, 5, this is the 6th, 7th, 8th, 9th. You'll notice that from the corner itself that we chose, you never connected to the 2 sides that were right next to it. And that's because they don't make a triangle, they just make straight lines. So in order for us to figure out how many triangles we're actually going to connect, so down here at the bottom where the 7 comes from, it is the number of sides, which in this case was 9, minus the 2 corners that you don't connect to. And then again, drop down the 180 for each triangle. So when we go through and we type this in, then our total is actually going to be 1,260 degrees. So if we add up all of the interior angles, that's what we're going to get. So knowing that we don't necessarily need a picture for this, we should be able to do the next problem. So a 17gon is going to have 17 sides. You're not going to connect to the 2 corners right next to it. So we're going to take the number of sides and we're going to decrease it by the 2 corners that we're not going to be doing. And then we're going to times it by the 180, which represents the sum of the angles in a triangle. If we multiply that together, that's going to give us 2,700 degrees. So again, that's if you add up all of the corners inside. Regular decagon. Okay, I wanted to take a look at this using the vocabulary idea. A decagon is a 10-sided polygon. So this is a 10gon. Now that we know that it has 10 sides, we can go ahead and use the same idea. So 10 minus the 2 corners you don't connect to, because they don't make a triangle, they're just straight line segments. And then we would take our 8 times 180, and that's going to give us 1,440 degrees. Now, it doesn't matter if your polygon is regular or not at all. So you'll notice on B, it was a 17gon. It doesn't matter if the sides are the exact same length or not. We're talking about if you add up all of the angles together. Okay, now moving on, calculate the measure of each interior angle. If we are calculating each interior angle and we aren't necessarily given a picture, so take a look at B, we have to be told that it is regular. We have to be told basically that all of the interior angles are going to be congruent, all of the exterior angles are going to be congruent, and all of the side lengths are going to be congruent. So if we take a look at this, the measure of each interior angle, all right, so basically what we're looking for is we want to figure out how big that orange angle is in that first picture. Well, I'm going to go through and do the same thing. I'm going to figure out what the sum is first. So I want to do the sum of the interior angles. Well, the sum is dependent on the number of side lengths, or number of sides, and then minus 2, just what we did on the previous slide, and then times by 180, because this represents all of our triangles. So we're going to go through and we want to count these sides. So what we have here is a 14gon. So I'm going to plug a 14 in for n, times by 180. Okay, 12 times 180 is going to give me the sum of all of the angles. That's going to be 2,160 degrees. However, I want to find each one. So what I'm going to do is I'm going to take the sum and I'm going to split it evenly to every corner. Well, since this was a 14gon, then this 2160 gets split evenly to all 14 angles. So if we divide that by 14, we're going to get an approximation here for each angle. It's going to be 154.2857 degrees. Okay, same idea here with B. So we have a regular, that's good, 26gon. All right, let's find the sum first. So we're going to do 26 minus 2 times 180, and then that sum is going to be split evenly to every corner. Well, there's 26 corners. So if we type this in, we're going to get 24 times 180, and then we're going to divide that by 26. We're going to get another approximation here, which is fine. That's going to be 166.1538 degrees. So again, we can only find each interior angle if we are told that it is regular, or we are given a picture where we can actually solve for x or y or z or whatever is identified for us. Okay, moving on, question number 3. I'm going to calculate the sum of the exterior angles. This is my favorite one to do because the sum of the exterior angle is not dependent at all on how many sides your polygon actually has, because the sum of the exterior angles, regardless, is going to be 360 degrees. It doesn't matter. It does not matter at all how many sides or angles you have. It doesn't matter if it's regular or not. We can find the sum is guaranteed every single time 360 degrees. Now, much like what we did previously with the size of each interior angle, we needed it to be regular, or we needed some sort of a picture to be able to actually solve for a specific angle. Same idea here. If we're talking about the measure of each exterior angle, we want it to be regular. But it's the same idea. You're going to take the sum, so whatever the total is, well, we know the total is always going to be 360, and you're going to split it evenly to each one of the exterior angles. If it is a 15gon, that means that there are going to be 15 of them. So if we divide, it looks like this is going to be 24 degrees for each exterior angle. Okay, same idea. Oh, a little bit of vocabulary here. An octagon is an 8-sided polygon. So make sure that you know your vocabulary here. Same idea. 360 degrees is the total. We want to split it evenly to each one of those exterior angles. If we divide this, this is going to be 45 degrees. Okay. Question number 5. We want to calculate the area of the regular polygon. All right, so we want to take a look at this. Now, one of the things that we talked about in class was the idea that you may be going back and referring to some trig knowledge that you have, but you also may be going back and referring to some special triangle knowledge that you have. So if it winds up that you have a 30, 60, 90 triangle, the expectation is that you will use that special right triangle to answer the question. You won't give decimal approximations. Whereas if you end up with like a 72 degree angle, well, nothing special about 72, nothing against 72, but it's not a special angle. So we would use trigonometry to actually be able to find the lengths there. What's important too, though, is you want to make sure that you don't use a rounded answer or truncated answer to get another answer. So make sure that as you're typing this into the calculator, you go back and retrieve those exact value answers that you were using previously. All right, there's a couple different ways to do this. I'm going to do this with a dissection and using all the different triangles. So we want to identify where the center of the shape is. So just kind of eyeball where the location is here. And then from there, we're going to draw our triangles that go to each of the corners. I do think it's important for people to identify that all of these triangles are going to be 100% congruent to each other. So if we can find the area of one of these triangles, then we can actually find the area of all of them put together. So let's just find one. So I'm a big fan of actually taking out the bottom triangle here. So if I'm going to take that orange triangle out off to the side, Just put some measurements in here. Just want some more space. Again, the picture doesn't have to be drawn to scale. This is just a tool to help you. So there's my orange triangle. I do want to make sure that I put in the height of this thing, since that's one of the things I absolutely have to be able to find or calculate the area of a triangle. So here we're talking about the area formula for a triangle. In order to find the area of a triangle, you want to make sure that you have the base and the height. Well, the base and the height are perpendicular to each other by definition, actually, in any shape. So I need that perpendicular business to happen. Okay, additionally, I'm going to take some of my measurements back from the other picture. I know that the side length is 14 units because it was given to me in the picture over here. So that means that the entire base of this triangle is 14 units. However, I'm only going to be dealing with either the left or the right side of this. So I'm going to go through and identify that as 7. So as when the height came down, we know that this was an isosceles triangle to begin with. When the height came down, you actually bisect or cut the base in half, which is actually kind of nice. Then we are definitely going to need the apothem, which is the height of this triangle. So I'm going to go ahead and call it A. We do need to figure out what angle we want to use, and this is kind of a personal choice. So if we go back to the actual polygon, you have multiple angles that you could find. I think I'm going to use the one up at the very top there. So to find that angle, I know that all of these triangles, well, let's see how many I have. 1, 2, 3, 4, 5, 6. Okay, I have 6 triangles. Those 6 triangles, so those 6 angles up at the top, when you put them together, are going to equal 360 degrees. So what I'm going to do is I'm going to take 360 degrees, and I'm going to split it evenly to each one of those triangles. That's going to give me 60. But if you take a look at the triangle over here, so the 60-degree angle in my triangle was that whole thing. I'm going to chop it in half, much like I chopped the side in half. So I'm going to take the 60-degree angle that I just found, and I'm actually going to divide it by 2. That's going to give me 30 degrees. All right, looks like we have a special triangle. So this is going to be 30 degrees, which means we know that this is going to be 60. Okay, using my knowledge of special right triangles, I know that the smallest side is 7, which means my medium side is actually going to be 7 root 3. So taking a look in my picture here, I know this is going to be 7 root 3. Now, if I needed to know the radius is from the center of the object, so back to my polygon, from the center down to every corner. So it's that green line segment that's in there. That's identified as the radius. So a little bit of vocabulary here. So if I needed to find the radius, going back over to my orange triangle on the side, drawing in my green line segment, we know that that is going to be 14 using our knowledge of special right triangles. All right, so I have enough information now to actually find the area of my orange triangle, the whole orange triangle. So to find the area of the orange triangle, I'm going to do the base. Well, the entire base was 14 times the height. Well, the height was the apothem, which is going to be 7 root 3. And then, don't forget, it's a triangle, so we need to divide by 2. If we do that, we'll notice that the 14 and the 2 will simplify to 7 and 1. So I think the area of our triangle is actually going to be 49 root 3. Now, I'm not going to type this into my calculator because I don't want to get an approximation for that root 3. This was a 30, 60, 90 triangle. I want to make sure that I stick with the exact answer. All right, now let's actually think back to the original picture. So the original picture itself, we had a whole bunch of these orange triangles. Well, we need to ask ourselves, how many of those orange triangles do we actually have? Well, we've got 1, 2, 3, 4, 5. We have 6 of them. So in order to find the area of the, all right, 6-sided, this is a hexagon. We're going to do 6 times the area of the triangle because we have 6 triangles. So now we want to do 6 times, and then go ahead and plug in your 49 root 3. As a reminder, when we multiply these together, we can multiply the 6 and the 49, and we're just going to kind of take the root 3 with us. So this is going to be 294 root 3. We were given inches on this, so this is inches squared. So this is the area of our hexagon. Okay, moving on, B, we have a regular decagon with a radius of 7 centimeters. I'm not going to necessarily draw the decagon. I just need to know that the decagon itself is a 10-sided polygon. So I know this is 10 sides, which means I am going to get 10 triangles out of it that originate from the center. Now, I'm just going to draw one of them. So if I draw one of the triangles that we're going to use, again, not drawn to scale, I just want to have some sort of a visual representation, kind of help myself out here. I definitely need the apothem because that's the height of this thing. Get rid of the excess there. I know that that length is going to be the apothem. Okay, going back to what was given to me originally. Well, what's given to me is the radius of 7. Remember, the radius goes from the center to the corner of the decagon, which in our triangle is always going to be our hypotenuse. Okay, from here, we need to be able to find the angles. Well, you can find a whole bunch of different angles. I think I'm probably going to stick with the very top corner, though. So, same idea. So I'm trying to find this angle that I just marked in black. All right, so I know that that comes from the center, which is 360 degrees. This is a decagon, which means there are 10 of these green triangles, which is 36 degrees. However, that's the whole thing up there. I'm going to take that 36 degrees and I'm going to cut it in half. So that's going to give me 18 degrees. All right, so this corner up here is 18 degrees. 18 degrees is not from a special triangle, which means we're going to need to use some trig. So we're going to need the apothem since that's the height of our triangle, but additionally, we're going to need the base here. So I'm going to go from here to here and identify that as B, just as my base. You could call it whatever you want. I'm going to end up doubling it to actually get the base of the green triangle, though, so I don't want to get myself too confused with the orange base that I'm identifying and the actual base of the entire green triangle. All right, let's go ahead and write our stuff up. So let's go ahead and find B first. Well, from the 18, the B, and the 7, it looks like we have sine. So we're going to do sine of our angle, which is equal to opposite over hypotenuse. I'm going to cross multiply. That's going to give me 7 times sine 18 is equal to B. Now, you can go through and get the approximation of this, but we're not going to use the approximation to actually find the answer. I'm going to use 7 times sine 18. So I'm not even going to type it into my calculator. I mean, you can, but you don't have to. All right, let's find the apothem now. Okay, so the apothem, I'm going to use A, 18, and 7. That looks like cosine to me. So I'll do cosine of my angle 18, which is equal to adjacent over hypotenuse. Cross multiply. That's going to give me 7 times cosine 18, which is equal to A. Same idea. I know I'm going to use the exact value. So if you type these into your calculator, that's totally fine. Just make sure that you arrow back up to it in your calculator and you select the actual answer, not some rounded version or truncated version of it. All right, now let's actually find the area of this green triangle. So the area of this green triangle is going to be, okay, well, we need this green base, which is technically 2 of the oranges. So the base of this triangle is 2b. I'm going to go ahead and put a box around that because I'm going to type it in just a second, times the height. Well, the height is the apothem divided by 2. Oh, what's nice about this is that you can see the 2's actually cancel. So this works out. Oh, I need to put a box around the A as well. This works out that really what I'm doing here is I'm just multiplying B times A. So I'm going to do my answer from B and my answer from A, and I'm just going to multiply them together. And let's see what we get here. And the approximation for this is going to be 14.4007. Now I'm going to do the same thing that I did. I am going to make sure that I hold on to this answer. I'm not going to use the 14.4007. I am, however, going to use that exact answer to be able to find the area of whatever polygon this is. And it looks like we are finding a decagon. So of a decagon, well, that's 10 of them. So we're going to have 10 of the triangles. So take the answer from your triangle as it resides already in your calculator, and let's go ahead and just times it by 10. If you times it by 10, we're going to get 144.0073. Were we given any units? Yes, we were. We were given centimeters. So this is centimeters squared. Okay, the last type of stuff that we've done, got a couple of slides on this, so we want to be able to state the ratio. So one of the things that's important to note here, we're basically dealing with two ratios. We are dealing with the side and the perimeter, and I am going to group them together because their side and perimeter ratios are both identified as R. Then we have the area ratio. The area ratio is the same ratio as the other two. It's just that it's squared this time. So I want to find the perimeter ratio given the side ratio. So if my side ratio is 4:7, that's R, my perimeter ratio is also R. So it's actually going to be the same. So my answer is 4:7. Go ahead and box the answer here. Okay, the next one, the area ratio. All right, we're trying to find the area ratio. We know the perimeter ratio. So the perimeter ratio is going to be 9:11. Well, the area ratio is R squared. So we're going to take this ratio and we're actually going to square each of the numbers. And we know that 9 squared is 81, and we know that 11 squared is 121. This is my area ratio. Okay, we want to find the side ratio knowing the area ratio. All right, so area ratio. Well, the idea here is that in order to get the area ratio, we had to square it. This is a squared. So what we're going to do is we're actually going to square root each of those. Well, I know the square root of 144 is 12, and the square root of 9 is 3. That's going to be my side ratio. That's also my perimeter ratio because side ratio and perimeter ratios are the same. Okay, let's take a look at some applications. So two figures have a ratio of similarity of 3:4. Okay, a ratio of similarity is the same thing as the side length ratio, which is also the same as the perimeter ratio. If the area of the larger figure, okay, I'm going to start using fractions for this. So I'm going to take my ratio of similarity and I'm going to rewrite it as 3/4. You could write it as 4/3 if you would like. Doesn't matter. Notice that in this fraction, I put the smaller number on top and the larger number on the bottom. I'm going to stick with that. So I put small on top. I know this based off of the relationship of the numbers 3 and 4. All right, now I'm going to use the area ratio. Okay, I need to change this. So I'm not going to put an equal sign here. I'm just going to draw an arrow. This is a side length ratio, which means right now this is R. I need to turn it into R squared because I'm trying to get areas out of this based off of the question. So let's go ahead and square these guys. So that becomes a 3 squared and a 4 squared. All right, let's clean that up. So our R squared is going to become 9/16. All right, this is the ratio that we're going to use to be able to answer this question. So I want to use that because the next part of the question has specifically to do with area. All right, so let's use our ratio here. So I've got 9/16. This is R squared. Notice the number on top is small. The number on the bottom is large. Just make sure we keep it organized. Equals. All right. We know that the area of the larger figure is 100. Well, larger number goes on the bottom, so put the 100 on the bottom. We're going to find the area of the smaller figure. I'm trying to figure out what that is. So I'm now going to solve this. Remember, go back to stuff that we have done previously. In order to solve this, you might want to cross multiply. So we get 9 times 100. That's going to give us 900 is equal to 16 times x, which is 16x. We'll go ahead and solve. Let's divide by 16. Those simplify. We're going to get x is equal to 900/16, but let's go ahead and type this in and see what we get. Now, we know that this needs to be smaller than 100 because it said that the area of the larger one was 100. So this is going to give us 56.25. which is definitely smaller, and this was units squared. Now what you can do to check, you don't have to do this, but what you can do to check this is take your 56.25 and put it over the 100. You want to simplify this. If you do 56.25 divided by 100, and you turn that back into a fraction using the calculator that we have, this is going to give us 9/16. It should match r squared. So that should be r squared. If it isn't, you made a mistake. You need to double back and fix your work. Okay, number 8. And this is going to be our last one. Pentagon has an area of 45 units squared. If that pentagon is enlarged with a side length ratio, all right, here we go. A side length ratio, which means r is 3. And then area, okay, this is an area problem. All right, we need to turn this into r squared. So r squared is equal to 9, because I did 3 squared. So I'll show my work there so we can see where that came from. So if the original area was 45 and we were trying to enlarge, so we're being told to blow it up, so we are multiplying by our new area ratio, which is 9. Let's go ahead and multiply those two together, and it looks like we're going to end up with 405. That is going to be the new area of our figure.